When we have gases, it's possible to put more than one gas in a container, and we will encounter this very often. Even right, the air that we breathe is multiple gases in this one container, and we can still do calculations and figure out what's going on with each gas in the sample because of Dalton's law of partial pressures. So Dalton's law says that each component exerts a partial pressure that contributes to the total pressure. So, right, I have this is my container. It's completely empty. There's absolutely nothing in it. And I'm going to put three different gases in here. So I have some pink dots to be gas A, green dots to be gas B, orange dots to be gas C. The pressure of gas A, so I've got that labeled PA, it's the number of moles of A times R times T over V. So still ideal gas law for A in a specific container, this is the pressure of that gas. For gas B, the pressure of gas B would be the number of moles of B times RT over V. And for gas C, the pressure of gas C would be the number of moles of gas C times RT over V. Right? The individual gases, I can look at them individually. If I know how many moles there are, I can calculate the pressure. Now, the total pressure in this container is the pressure of A plus the pressure of B plus the pressure of C. So this is, right, Dalton's law of partial pressures says that the total pressure is the sum of the pressures of the individual gases. Now, because algebra, I can also rewrite this. Like I can do some substitutions. Instead of saying PA plus PB plus PC, the pressure total, I could also write it as the number of moles of A times RT over V plus the number of moles of B times RT over V plus the number of moles of C times RT over V. And right, RT and V are the same for all three. So the total pressure could also be calculated as the sum of the moles times RT over V, or N total times RT over V. So the identities, when we're treating everything with the ideal gas law, the identities of these gases don't matter because they don't stick to each other, they don't have any volume. If they have a collision, it just bounces off perfectly. Everything's in continuous motion. So we could just do essentially the ideal gas law where it's the total number of moles. And from that information, if I needed to then back out into a partial pressure of A, B, or C, depending on what kind of data I can collect, I can use those relationships to also get me to those pressures. Related to this, we will calculate something called a mole fraction. Now, this is going to come back in next semester, but right for here, we can calculate it. And I've got the same relationship three different ways to show how they're all interconnected. So the mole fraction is the number of moles of one component divided by the total number of moles. So the mole fraction of gas A is the number of moles of A divided by the total moles. Because of Dalton's law of partial pressures, the mole fraction of A is also the partial pressure of A divided by the total pressure, which means that if I knew the mole fraction and the total pressure, right, any combination I can fill in and solve for the leftover variable, I can get the partial pressure of A if I know the mole fraction of A and the total pressure.